Welcome everyone. This is actually an addition to the reference frame transformation video that I had. I have posted already because there are some questions about the different rotation directions and how the alpha beta alignment can change the transformation when you do reference frame transformation. So there are many approaches out there. So I wanted to highlight some of the differences and show how you can align the frames when you perform a reference frame transformation. It always depends on how you apply it. Different regions, different companies, different people use this transformation differently depending on how they learned it. So I wanted to show you some of the differences. Again, if you haven't seen the previous video, please feel free to go and review that, take a look at that. And I primarily rely on analysis of electric machines, text. I go by the notations they use by Paul Krauss. So the text analysis of electric machines by Paul C. Krauss, Professor Sudoff, and Professor Pekarik. So, that's a good text, very practical, very useful in terms of the theory. And I'm trying to help digest some of the material here. They do stick to a certain notation, but I do want to show what are the differences that you're going to encounter. Now, when you look at reference frame transformation, depending on what material you look at, you're going to see two primary directions or phase, the three-phase, I want to say the vector sequences, okay, or arrangements. So one, if you have it in this combination, you have the sequence or the space vector rotating in the counterclockwise direction, like that. And then if you have the following sequence, you are going to come across the rotation in this direction. Now, I've seen people call them positive and negative sequences. Technically, that is not true because the definition of positive and negative sequences are a little bit more deeper, a little bit more different. So I'm not going to call them positive or negative sequence. I'm going to call them counterclockwise and clockwise rotation of the space vector. Okay, because that is what this ideally represents. When your currents are varying in this manner, you're going to see either a counterclockwise rotation or a clockwise rotation. Now, this direction of rotation is crucial because your theta, omega t is your theta, and that theta is what we use to align our reference frame, right? So we have two axes on our reference frame that we rotate, and that's very important in our alignment. All right, so phase sequence is very important. In my previous video, I only used this approach. This is the only one I showed. Now, when you go into clock transform, so basically in clock transform, you have your alpha and beta axes depending on how you choose to define your positive and negative directions for alpha and beta. Those two axes are fixed. They are on the stationary frame. They are not rotating. Okay. So what you are essentially looking at is, as the space vector rotates in the chosen direction of your interest, depending on how your phase sequence is set up, you're basically looking at the projection on alpha and projection on beta, right? Meaning you are looking at how those projections are varying. So if you think of the counterclockwise rotation, right, and if you assume the vector starts in alignment with alpha, f alpha, as this rotates, the projection on alpha reduces and projection on beta increases negatively. See, because we defined positive direction in this way. Therefore, since the vector is rotating in this direction, you have it increasing negatively, right? And if you think of a clockwise rotation, you can see that even though F alpha is reducing as it rotates, right, the projection on F alpha reduces, the projection on F beta increases positively because it's rotating in the opposite direction. So this is important. So your projection, the projections of the vector, the change you see in the projected components change depending on how you define your F alpha and F beta. That's the first step. And this is not always the same, but practically speaking, you have to look at the underlying equations that you're using. And of course, you can generate all your equations based on a particular F alpha and F beta alignment or definition that you choose. And you can go back and check the previous video on how to come up with those. Okay. The key takeaway here is you can define F alpha and F beta in any direction as long as you mathematically account for that proper alignment when you go from 3 components to 2 components, essentially the projections. Okay. And then the second thing that you have to consider when you apply DQ, going from alpha beta frame to DQ frame, you have a rotating frame now. In alpha beta, it's a fixed frame. You're in stationary frame. When you go to DQ, that's a rotating frame. So when you have a rotating frame, you have to make sure your frame is rotating in the same direction as the vector. Otherwise, your reference frame transformation will not work. That's important. Okay. And then in my previous video, if you recall, I aligned my Q axis along with the vector. Okay. So it's a little, it's up to me. It's up to the user to how to align the vector. But by definition, one could argue, quadrature axis, Q axis, how can you have your vector aligned to the quadrature axis? So if someone wants, you can actually align your vector along the direct axis, but there's no mathematical limitation in aligning Q axis with the vector. But be careful when you go into standard notation for electric machines. There's a standard form that you have to follow when you align or when you define what is Q axis, what is D axis, right? Because you have to align your D axis along the rotor flux or the stator flux, depending on what you define, what you're looking at with respect to. Is it the machine flux you're looking at from, or are you looking at the rotor flux? Okay, so just be careful when you look at the different equations in applications. Okay, all right. Yeah, in synchronous machines, we typically define rotor flux along D axis, and then we apply Q axis, which is the stator flux, 90 degrees out of phase to generate optimal torque. There's no saliency. Just keep that in mind. So in order to shed some more light on what this what we talked about just now, I'm showing here, I'll show you some simulation, but I want to show you what are the 4 cases that I'm going to show simulations on. So here I have what we call the counterclockwise rotation, and here we have a counterclockwise rotation, and here we have 2 clockwise rotations, and I'm aligning F alpha and F beta in this fashion. In the first case, I'm aligning F alpha and F beta, or at least I'm defining F alpha and F beta in the following way. Okay, but still the direction of the space vector rotation stays the same. Now, when I go apply my DQ transform or Park transform, I'm aligning my Q axis along the vector in both cases. So Q and D alignment with respect to the vector stays the same in both cases. Okay. And if you look at the second set here, I have clockwise rotation. I define similarly to the previous case, I define F alpha and F beta. And again, I have FQ and Q and D, Q and D aligned, Q aligned to the vector, D 90 degrees out of phase, and it's moving along with that vector, right? Now, when you implement them, for you to get consistent results in doing rotor reference frame transformation or reference frame transformation, you need to accommodate the equations, the transformation equations, to account for the different axis alignments. Okay, so going from ABC to alpha beta will change here versus here, and here versus here, and so they're going to be different in each case. And going from alpha beta to DQ again is going to be different because of one, the axis alignment, as well as the direction of rotation. However, once you account for these in your underlying equations, you're going to get the same result. You're going to get the same result. So let me pull up my simulation here. I can find my cursor here. All right. So hopefully you can see these are the four cases I'm again looking at, and you can see that this is rotating in clockwise the direction, and then this is going in the counterclockwise direction. You can see the negative slope there, right? And then I have same ABC phases feeding into these alpha ABC to alpha beta blocks, and then going from alpha beta to DQ. Okay. Now, what's different? Here, the alpha beta, in these two cases, the alpha beta definition is different. And then between these two sets, the rotation, direction of rotation is different. So now, if you go look at the plots, what you'll see is that you're going to see they get same results. They get same results. Try to get all the scopes open here, and they're going to look the same. I can minimize this a little bit. Yeah, very interesting, very interesting, and this is going to be a little bit more mind-boggling for some of you. So just think about the concept and try to understand what we and how we use this reference frame transformation in our analysis. Because see here, even though we are looking at two different rotations and you are looking at different alpha beta axis definitions and alignments with respect to QD, you get same q-axis voltage or q-axis amplitude in all four cases, right? So this is where this is the tricky part when you work with synchronous machines or reference frame transformation. You need to understand how you define your alpha beta, and then which direction the vector is rotating, and how you relate your alpha beta projections onto your quadrature and direct axis, and what do you define as quadrature and direct axis. Okay, so there are some key elements here that you need to understand. You can go through this couple of times and try to understand, and you can I'll try to show you here in each case, right? My relationships are different. The equations that I use are different just to account for the difference. You can see here, see the signs are different. Okay? See, signs are different. Okay, same goes for the reverse rotation. You can see the signs are different. Right, the signs are different. Okay, so very interesting topic. So thank you for watching. Please feel free to ask more questions. This arose from a question that someone posted, so very thankful for that. Hopefully you folks can ask more questions, and I can try to create some more of this material. Okay, thank you.